Hey, hope you're doing well. Wanted to do an update video here. This is for the year 2024 developments in NAP. In terms of amateur energetics, NAP is starting to get picked up. People are developing interest in it, and they're sort of ready to move past the native crystal form that you normally get when you slow crystallize NAP. That method is covered by the old NAP video with slow crystallization, producing these large, elongated, beautiful blood red crystals. They're they're powerful. They're really pretty. They're not exactly usable in terms of something that can be poured into a detonator body. They're extremely sensitive. When the crystal breaks, it's sensitive to detonation. So both friction and impact stimulation readily cause detonation with crystal NAP. Being as how NAP, it has no published scientific literature, all the development has been done on the internet, on YouTube, websites like Science Madness. The development of it is going on in amateur energetics. The original inventors put out their patent on general aminoguanidine complexes, but there's not anything else published besides that, and they're not sharing personal IP if in fact they are continuing to develop it. So this video is going to be updates on the development of NAP with other variations that are high performance and give a lot of tailored characteristics that are very useful in the application of NAP. So I hope you'll enjoy this.
Energetic America.
Explosives aren't hard to make, guys.
Accelerate.
Now the synthesis procedure, it is evolving all the time. What I'm doing right now is totally different than 5 months ago or a year ago. It's just always changing. One of the updates that I've made across the board for any water solvent method of producing NAP is to reflux with a cover. I usually use a watch glass. I just throw it on top of the beaker, and this is going to elevate the homogeneous temperatures within the reaction to keep them consistent and not have so much interference from atmospheric conditions or variations. When refluxing covered for the reaction for NAP to take place, the heat intensity is increased. You can reduce the time a little bit closer to 5 minutes rather than 7 minutes, which, if you do uncovered, 7 minutes is going to give you a slight additional yield. 5 minutes is fine for a covered reaction. The other update for water solvent methods, what I'm using in my procedure is cheap nickel carbonate, from ceramic supply shops. So this is very inexpensive. You can get it, it's average around $20 a pound. Ceramic supply shops are all over the place, especially in the United States. So it's very convenient to be able to just buy for $20 a pound the nickel carbonate instead of producing it yourself, which would be a lot more intensive in time. The downside of using ceramic nickel carbonate is that you're going to have impurities in there, and those translate into undissolved solids in the bottom of your reaction. There's also probably some nickel carbonate itself that isn't reacting in the reaction. It's not a very efficient reaction, especially when water is used as the solvent. And what you'll typically see is at the end of a reaction, you'll see a separation, both a solvent layer of liquid and unreacted solid materials at the bottom. So the second update to the procedure is that the liquid fraction is decanted. It's just poured into another vessel immediately following the reaction. So we're pouring it off. We're leaving behind unreacted solids in the reaction vessel, separating the two. All of your crop of NAP is going to come out of the liquid portion. Anything that forms on the unreacted material is going to be negligible. And it's been found that in crystallization of NAP out of the liquid, you get an immediate crop somewhere between 20 minutes to 4 hours. You'll get the initial crop of NAP, but then over the next 24 hours, you'll subsequently get additional production of the crystals. So I wouldn't dump out your liquid. I would save that and allow the full yield to come off of it. With a water-based reaction based off of 1 gram of aminoguanidine, which is kind of the critical reagent that the ratios are based off of, because that's the most difficult material to procure. Out of that method, you get less than a gram typically when you're doing the water solvent method. So I'm talking 1 gram of amino guanidine into your reaction mix, and out of that you're going to get maybe 800 or 900 milligrams, something like that is what you're going to get for product of NAP typically. The mechanical sensitivity of the native water solvent NAP is going to be fairly sensitive. You're going to have impact and friction sensitivity. It's pretty sensitive. It's in range of other, sensitive primary explosives, so it's nothing outrageous, but it is sensitive. So in the development, one of the variations that I've worked on is introducing the reaction into other than water solvents. So I've used a lot of materials. I've done, the traditional means of capping agents to affect morphology, like with lead azide using, dextrin and carboxymethyl cellulose to try to affect the crystal size. Those typically don't work because the reaction is so sensitive to complexation. So then after that, I went into using other mediums, so other liquid mediums. Out of all the solvents tested so far, isopropanol is the most advantageous. It's going to give you a totally different product. What that means is that isopropanol is it seems to be complexing. I don't know exactly what's going on. It's probably an isopropyl group or perhaps 2. I'm not really sure. But you're getting a different color and you're getting totally different characteristics, so it's almost certain that IPA is complexing. So for differentiation, isopropanol solvent NAP, this is referred to as INAP. To keep it simple, keep track of the different variations here. INAP is isopropanol produced NAP. It is very different than crystal NAP, both in appearance and in mechanical character and in performance character. So in terms of its appearance, it's going to be a salmon colored powder. It's very packable, very pourable. It's much easier to handle and process than the large crystal form. Other benefits include the reaction yield is going to be substantially greater. You're going to get well over a gram out of each gram of amino guanidine put into the reaction when you use isopropanol solvent. INAP is it's got a lot of things going for it. Mechanical sensitivity is greatly reduced with INAP. Its mechanical sensitivity is among the best for primary explosives that actually fire on a heat stimulus, like on a fuse. There are some primary explosives that don't detonate very well, that are pretty insensitive, but they're less usable, right? So the INAP is probably in the range of 3 to 4 times more insensitive than the native crystal, and that's to impact is what I'm talking about. So in friction sensitivity, in my testing, I have not been able to even get INAP to detonate under a 4-pound hammer friction grind, the old-fashioned way, which says a lot about its insensitivity. Stability of INAP is very good in terms of monitoring experiments. There's a sample that's been going for over a year. It's totally unchanged, so it's it's very storable. Things are looking really good for INAP. Now, one of the detractions, or it could be a positive, I suppose, depending on how you look at it, INAP its firing efficiency in terms of initiating a detonation it's less efficient than the crystal form of NAP, and then the other advanced variations that we'll talk about next, it's significantly less efficient. So the minimal masses required to fire common secondary explosives, ETN, RDX, PETN, you have to really have somewhere over 25 milligrams minimum to get those to detonate. That's what I've found. Now, that's not to say that INAP is somehow, weak or anemic or inferior. It's one of the most powerful primary explosives that you can use. But comparatively to the other variations, it's you have to use a slightly more mass. So it kind of puts it in the range somewhere around lead azide performance to maybe DDMP, somewhere in between there in terms of the masses that you would use to fire, a base filler in a detonator. So what is the present procedure for producing INAP? It is identical to water solvent NAP production. The difference is that you're going to switch out water for isopropanol. I use in all my experimentation drugstore IPA, drugstore isopropyl alcohol in the 90% range, and that works very well. So stepwise, we're refluxing isopropyl alcohol until it reaches a boil. Its boiling point is lower than water, so it's going to achieve that boil quicker. It's also got a higher vapor pressure. and it boils off a lot quicker. When you're using IPA solvent, the main difference is that you want to use a little bit more, because the last thing that you want when you're producing this is for your reaction to run dry and run out of solvent. You don't want that to happen, because you're going to heat the material to dangerous levels. Now, NAP, INAP, they all detonate somewhere in the range, somewhere around 270 C. So on your hot plate, when you're heating your solvent, you want to keep it below that threshold so you have a margin of safety. So I wouldn't throw the heat all the way to the max trying to rapidly heat the solvent. I would allow it to slowly heat at, I don't know, somewhere around 200 C, something like that, just well below the threshold of 270, so that you don't have a detonation if something happens, an emergency, you have to walk away, whatever, just to give a margin of safety for error. So once the isopropanol is boiling, I use a cover to bring it to a boil. I remove the cover, I dump in all of my reagents all at one time, recover, and then allow it to reflux for 5 minutes. The color change sequence is a little bit different with INAP, and the reaction mixture is going to be homogeneous. You're not going to have a liquid layer and solid layer. Typically, it's just going to be a homogeneous single color product that you're going to get. At the end of 5 minutes, you remove it from heat. You don't need to decant. You just pour off the entire thing onto a coffee filter so that you can filter it off. INAP dries extremely quickly because of the vapor pressure of isopropanol. It's going to dry a lot faster than the water solvent version. Yet another advantage of INAP is that you can go from, mixing up your reagents to firing the INAP in record times for primary explosive. It's one of the fastest to produce, so it has a lot going for it. Where INAP stands as a technology is that it's going to offer you, comparatively higher yield than standard NAP. And the big advantages over, something like lead azide is that typically you have to dope lead azide to get the sensitivity to heat stimulus, to flame stimulus, or an E-match or something like that. You have to dope it with, a sensitizer, tetrazine, or lead styphnate is what is most commonly used. So these are you're starting to get into multi-material concoctions. It just becomes increasingly complex in terms of finding the perfect secret sauce for a detonator. INAP is not like that. It's a mono-material primary explosive. In fact, you can use it to charge the entire detonator with INAP if you wanted to. But you can easily use INAP as the initiating charge and the primary charge to then kick off your base charge in your detonators. It's going to supplant the traditional binary composition that they use for primary explosives, primarily being lead azide and lead styphnate. It replaces that. So that's where it stands. Let's talk about the most exciting development in NAP technology, which is going to be what's called UNAP. UNAP is a short abbreviation for ultrasonicated NAP. This is a crystal modification technique that produces a very dense and extremely tiny crystal for NAP when it precipitates. The size of the crystal is unknown at this time. I don't have a way to measure that. It's extremely small. It's one of the smallest powders that I have. So if it could in fact be something like a nano powder, I have no clue. It's very small. How this probably happens is that the boundary layer of the crystal as it's forming gets disrupted by the ultrasonic frequencies. 42 kilohertz is what I've used in all of my testing in order to achieve this. The effect is that you get UNAP drops out of solution under ultrasonication in under 10 minutes. And the handling character of this material is vastly superior to something like crystal NAP. So in terms of packability and pourability, it's just far better. Now, in terms of what's really exciting about UNAP is that because similar to a detonator, for instance, a large detonator will always produce a bigger boom, but a small detonator is more efficient in terms of its size per output. And it has something to do with the surface area, of the shape of a cylinder. The same is true of this ultrasonicated NAP, the UNAP. You are getting incredible efficiency in detonations. So if you take, for example, a standard NAP crystal, they do detonate in single crystals. So you can take a single crystal of NAP, heat it to detonation, it will detonate. It typically doesn't have the brisance to puncture or perforate aluminum foil. Now, very high performance primary explosives like some of the more usable tetrazole, silver nitrotetrazole, things like that, you'll be familiar with using extremely minute masses and being able to have enough brisance to perforate foil. But Crystal NAP, it doesn't get there. UNAP is a totally different story. So UNAP is incredibly efficient in its detonation. It detonates in extremely small masses. I mean, we're talking, way lower than any of my scales go. I mean, we're well under 1 milligram masses, and we'll get perforations in aluminum foil. This is highly desirable characteristic for a primary explosive, and UNAP is the highest performance variant that I've worked on thus far. This is kind of the meat and potatoes of this video, is me describing to you the significance of UNAP. It's a very significant development in primary explosive technology. Like I said, the handling character is very good. The sensitivity profile is also very good. It is sensitive to impact. It's perhaps slightly less sensitive than Crystal NAP. It's practically the same, but where it really shines is in its friction sensitivity. UNAP is extremely insensitive to friction. It is possible to detonate it with friction, but it takes a ton of force. You have to apply a lot of grinding force in order to get it to go off. Nothing at all like the friction sensitivity seen with Crystal NAP. So the UNAP is extremely high performance. It has excellent handling and processing qualities. It is relatively insensitive in its response to stimulus. And it's incredibly efficient in terms of its the way that it detonates. In terms of firing actual secondaries, it's looking to be somewhere around 5 milligrams or above. You get a really solid firing at standard loads like baseline test loads that they use for lead azide, 25 milligrams, something like that. For an initiating charge, you're just going to blow stuff away. So with UNAP, you can get perforations in metal materials like lead blocks, lead ingots. You can get a detectable surface indentation somewhere around the 20 milligram mark. If you go up to 40 milligrams on a UNAP charge, you're going to get a significant impact witness on the lead block. It's very significant. With that, let's discuss the procedure for UNAP. So the procedure is identical to the standard liquid solvent version of NAP. You're going to boil water under reflux with a cover, remove your cover, dump in all of your reagents, and allow it to reflux covered for 5 minutes. At the end of 5 minutes, you remove the vessel from heat, and you're going to decant the liquid layer, leaving behind unreacted solids. The collected liquid layer is where your precipitation is going to take place. Before it begins to cool too much, you want to put it onto ultrasonication bath. For the ultrasonic bath, I use a very inexpensive, perhaps $20 jewelry cleaner that's in the 42 kilohertz range. That's what I've been using for all my testing, so that's what I would recommend in terms of the frequency that you should go after. It's very common for budget ultrasonic machines. So the ultrasonic bath is filled up at or above the level of the NAP liquid. You're going to put the beaker into the ultrasonic bath and run the machine. 10 minutes is all that you need. So within 10 minutes, you should see pretty much practically complete precipitation of what's going to come out in the UNAP morphology. It's a very cool looking process. It looks like little miniature clouds of explosions of crystals, materializing out of the ether in the reaction vessel. After 10 minutes of sonication, you're going to pretty much get everything out of it that you're going to get in terms of the UNAP morphology. What I do at this point is I decant the liquid again. You can decant it because UNAP will actually typically go to the bottom of the vessel and affix itself to the vessel wall. So you'll have the liquid layer on top of that, and you can pour it off. I would recommend keeping your liquid layer and allowing it to slow crystallize over the next 24 hours so you can get additional crop. The crop that comes out of it is actually affected by the initial ultrasonication to make it a very small crystal. So it's still extremely usable. It's just not the exact spec of the UNAP, but nonetheless very high performance, so I wouldn't waste that. I would save it and allow it to crystallize separately, keep them separate. For the ultrasonic bath, the reaction is extremely sensitive to the temperature of the ultrasonication bath. It should be ideally at ambient temperature. Somewhere around 20 C is what I've been using. So if your water gets too cold, it seems to cause issues with UNAP crystallization. If the water gets too hot, it also causes problems. When you're running an ultrasonication bath, it heats the water naturally. So within one batch, your water is going to elevate in temperature. So if you're going to produce multiple batches of UNAP, you would want to change out your sonication bath water to room temperature water every batch. For all variants of NAP, I use heat evaporation to dry out the material, Typically, I dry it at around 60 C is sort of my happy medium that I've found. I really like that temperature. It works really well. And that concludes the development updates of NAP. I'm really honored to work on this material and assist in developing it. Anything that I come up with that, findings that I come to that are worthwhile sharing, of course, I'll be sharing. But these two variations right here are extremely significant in terms of the technology of primary explosives. This is something that only comes along once in 100 years. In terms of industry, in terms of the government or military using them, in the United States we have the EPA. The EPA is very, they have an aversion to perchlorates in general. I don't agree with that. I don't think, I think perchlorates versus, azides or tetrazoles, anything like that, I think they're very, safe. In terms of what that means for amateur energetics is that, NAP, I predict will, I think it'll get extremely popular. It's one of the most simple primary explosives to produce, and it's extremely high power. The crossroads of having easy precursor materials and an easy synthesis route with having an extremely high performance primary, that's kind of a rare crossroads to come to, and that's why this material will likely supplant and push out other primary explosives over the years to come. Who knows? We'll be able to see in hindsight, but whatever happens, you saw it happen here first.